Good, then let's talk about the model where we combine it with fluid dynamics. And that model also has a name. It's called Model H, and just think of H as hydrodynamics. And now actually understand the confusion that came up in the first half with rho, the density, because I mean two different things. When you look at the particles, okay, there is a density of the fluid, which is still rho. And when I was talking about rho before the break, I actually meant the density of the Brownian particles in the fluid. Okay?
Test particles, kind of. We put in the fluid.
You can call them test particles, but they're not really testing things. They're actually embedded, and they are subject to dissipation.
Okay, so they interact.
They interact with the fluid.
So it's like you put some rice in hot water.
Or plastic beads into water, called colloidal physics. Okay? That's what people study when they study Brownian particles suspended in a solution. You can think of proteins in a liquid, that's the same thing. They are basically spherical. They don't look like so, but they may be, some kind of structure like so, but effectively they are particles in a fluid environment. And you want to study how they behave in a fluid environment, and you have to distinguish between the density of the fluid and the density that comprises the proteins or the particles. Okay. So in this model H now, I'll have those two fields. I have the density field of the particles, suspended in the fluid. I do have the density field of the fluid, and I'm going to assume in the following that we have an incompressible fluid, because water basically is incompressible at the scales one is interested in. So that means divergence of the velocity field that describes the fluid is zero. So that's the velocity field of the fluid. And that's it. Those are the variables that we consider. All the other ones are derived quantities. So what do we do with the equation of motion? So we will still have for our fluid a corresponding Navier-Stokes equation, dTV plus V nabla V, so advection, and that is equal to nabla dotted into a stress tensor, where the stress tensor has a form that's reflecting what's going on in the fluid. And remember, we needed all that in order for our system to show momentum conservation. And those are the terms that we have in a simple fluid that's subject to an incompressibility constraint. You only have the shear modulus left in the tensor and not the bulk modulus. Here's the hydrostatic term. And then you need to add the fact that the particles that you suspend in the fluid, they are acting on the fluid. Okay? And we will determine that part of the stress tensor later. And then, of course, you also have the sigma ij's, but they are the same. These noise terms are the same as before, because to linear order, nothing will change here in the noise terms. Okay, so it's hydrostatic. This is dissipation in the fluid. This is coupling to the particles, and that's the noise. And we have, to be complete, because of incompressibility, the divergence of the velocity field being 0. Well, what about the equation of motion for our density field of our suspended particles? They are conserved, they don't die, they're not born. So this needs to be minus the gradient, the divergence of a current that depends on position and time. And this current will have two contributions. And now this is a partly intuitive answer. One is clear. If the fluid is on the particles, it will advect the particles with them. Okay? Because we don't assume there's any kind of slip between the fluid motion and the particle motion, so they will be advected with the fluid. So this is a advection term, phi, the density of the particles times the velocity, and now no longer indicate the position and time in the arguments. And there will be a current that comes from the irregular motion with respect to this advection, and that's the diffusive motion of the particles. So there will be a term which is the diffusive motion, the dissipative motion that you have in the system. So in a similar way as we constructed here, a term that's coming from, here we have a term that's coming from the deterministic dynamics without any friction. Here, this is a part which comes in phenomenologically because we do have some dissipation. And here, in the same way, we have a part that's due to diffusion. And there we assume that this is given by minus a Onsager coefficient, L times nabla df d phi, where our f, the free energy functional of phi, has the structure of a volume integral over a local free energy part plus a half times kappa nabla of phi squared. Okay, so those are my equations of motion. That's for the particles suspended in the fluid, and this is for the fluid itself. Oh, sorry, I forgot the noise. So plus square root 2t times L times lambda as before, and this is f of phi. Right? So far, so clear. Now, let me ask you towards what kind of distribution function this should equilibrate to in the end. There's a kinetic part and there's a part that comes from this free energy. So it's going to be a Boltzmann-Gibbs distribution where the free energy plays the role of potential, and there is also the kinetic part. That's the probability distribution function this will converge to. Well, now let us calculate sigma phi, because that's the missing element that we don't have yet. And it should be such that momentum is conserved, and you can check later when we determine that this is actually the case. So what do we have? We have a second rank tensor because of the structure of the equations. That's important because that means there's only certain terms that will be allowed. And as you know, you have to take the tensors that drive that, and one tensor is the Kronecker delta, and there will be some coefficient A that we have to determine in order to get what this prefactor here is. And then in addition, there will be a tensor that you can construct from the scalar density that is just given by the product of the derivatives of phi with respect to xi and xj. And again here, there's a coefficient b that we don't know and that we have to determine. All right, so this is by symmetry, and there's no other choice that we can make. So what we do now is we think of our colloidal system in a coarse-grained fashion, right? So not as particles as I draw it, but as a field. So we kind of wash this out and think of this as a density field. And what we consider is a displacement field of those particles, and we call this displacement field u vector, and it will depend on where you look in space. Okay, there are certain constraints on this vector field. It's all embedded in a fluid. The fluid is incompressible, and that means the incompressibility condition is inherited. So the divergence of this u must be 0, such that this is possible. We can define a strain field like in elasticity theory. This is the analog of the gradients in the velocity. Here we have gradients in the displacement field. So di uj, and we call this here epsilon ij. And from elasticity theory, we take the corresponding expression for the free energy change that comes by those displacements. It will be given or determined by the strain field, and the response to that is the additional stress term that you have in the equation for the fluid motion. Okay. Now let's determine that. So when we look at such a displacement, then we will change the field phi of x. So we move this cloud here and displace it by x. So that means the corresponding field in the displaced configuration will be the one which is phi of x minus that displacement field. So to that order, to linear order, we will have phi prime of x, which is this here, minus phi of x. And this is minus u times the gradient of phi. Okay, now we have what this means. And we can calculate the variation of our free energy. Now in a second way, we can integrate over the volume, do the variation of the free energy with respect to phi, and multiply by d phi. This is the same as minus the integral over the volume, df over d phi is the chemical potential, mu, and we know what this displacement delta phi is. We just calculated this. This is u dotted into the gradient of phi. So we can compare the two terms. We now have the corresponding expression coming from elasticity theory that gives us the strain tensor in its general form, diuj, and that has to be the same as this one here, which is u. Oh, sorry, I'm rewriting this, what I have here. It has to be the same as that, but before I do so, I bring it in a form which is similar to what we just calculated. So I do partial integration, and that means this derivative on u will then act on sigma, and that's why I have a minus from that partial integration, u dot nabla dotted into sigma phi. Okay, and now we are done. We can compare the two, and from that determine what the divergence of sigma phi is. It is minus phi times the gradient of the chemical potential. We don't get sigma directly, right? We only get the gradient of that sigma. But when you look back here at our equation of motion, rho dv dt is determined by nabla dotted into the stress tensor. So all we really need is the nabla acting on the stress tensor. Great. So this means in total that nabla on our stress tensor is, so the forces here are due to gradients in the pressure, and then there's a contribution coming from dissipation, because we have just shear viscosity, eta is and the system is incompressible, that's the only thing we have. And then we have minus phi times the gradient of mu plus nabla dotted into the noise term. As a tutorial or an exercise, I'll ask you to show this. So sigma ij phi is given by the osmotic pressure times delta ij minus kappa di phi dj phi. Okay? And P osmotic is how the osmotic pressure is defined. That's the density times the chemical potential minus f of phi, where f of phi is the local term plus a half times the gradient of phi squared. Okay, so from the analysis that we showed during this class, the A coefficient was undetermined, the B coefficient we determined. This came out to be basically this coefficient here is related to this one when you do the math of rewriting this in terms of di phi and dj phi. And this I leave you as an exercise. All right, so together, we do get the following equation for model A, dt phi plus v grad phi, meaning the time change of the density field is a advection term. That's here on the left-hand side. And then on the right-hand side, we have a diffusion term coming from the drift due to gradients in the chemical potential, and a corresponding noise term. The noise term, well, how would you calculate it? It's the same as before, because this is also true for velocity equal to 0, and for that case we have determined the noise expression in this relation. And the second equation that determines the dynamics is the Navier-Stokes equation that is complemented by a term coming from the interaction with the colloids, which is this term. Here it's a minus gradient of the chemical potential times the density plus the corresponding nabla times the noise term, and the constraint under which we discuss this is that the fluid itself is incompressible. Okay, so that's our model H. Are there questions?
Yeah, so in the first line, if it basically is also a material derivative of phi, right? Because the divergence of v is 0, we can write it that way, but in the end it's similar derivative to...
Not quite. It looks like it.
Yeah.
But note the way I derived it. I say this is always true because you have to have a conservation law. And then I know there must be a mass current of the colloidal particles or the proteins that flows with the fluid. And it must be of the form phi times v.
Yes.
Now you take the divergence of phi times v. There will be two terms.
And the divergence v term is 0.
Yeah.
So that's the one remaining.
Yeah, that's why we, that's important here, because otherwise you would have another term here.
Mm-hmm. Okay, so it's basically a drift term along the velocity of the vector.
Yeah, so you can certainly think of this as a drift term, where the velocity of the fluid is carrying along the particles that you consider. Another tutorial I give you is show that momentum is conserved. You have all the tools available to you. I have shown this for the fluid. You just have to generalize that to this particular case. And now maybe you see the point here of the whole analysis. We do have a model B type of dynamics, a model A type of dynamics, where the fluid is just a passive surrounding that provides some friction. And then the dynamics that you have is only determined by the diffusive motion of the particles with respect to this surrounding fluid. This diffusive motion is characterized by a diffusion coefficient related to L by L equal D times rho. If fluid motion is important, and that's not always the case, because basically there's two scales here, right? There's a motion of the particles because they are moving by diffusion, and there's motion of the particles because they're moving by drift due to velocity. And depending on how strong the velocity is, diffusion will be or will not be important. If velocity fields are important, then you need to account for that by the fact that there's a mass flow as well. And the mass flow is driven by the velocity of the fluid. Well, and the velocity of the fluid is the classical Navier-Stokes, but let's say you can neglect the nonlinear term, then you would still have here the gradients coming from the stress tensor, and they are the new important part that determines the physics of this, is that there is a stress because of gradients in the chemical potential. And so fluid motion is driven by gradients in the chemical potential. That's what this says.
And in the free energy functional, can this also depend on rho and v? Or is it just interactions among particles of class phi?
So the v field is especially here, right? Because in the end, the velocity field will just show, density is constant, and the fluid velocity will be 0 in the end. And then this whole fluid dynamics equation is kind of irrelevant for the motion of the Brownian particles that you see. You will still have some kinetic part that comes in, but up to this kinetic part of the particle motion, the fluid dynamics in equilibrium is died out.
And so the free energy functional just kind of models interactions of the colloidal particles.
Yeah.
The kappa, I think the kappa came from the interaction.
Yeah, this is all just the interaction of the colloidal particles, and the system will relax to an equilibrium steady state where these colloidal particles have an equilibrium distribution that's described by their entropy in the surrounding fluid, by the stiffness that comes from the pairwise interaction between the particles, and then interaction terms that have been absorbed in this local free energy potential. All right. Good. Let's stop here for today. Yeah, question?
Do we also use the equilibrium state to find out how to perform the stochastic integrals, like which like Ito or other?
Yeah, that's the point I was mentioning. So if it's no longer on the board, but here it is, right? So if you are right here, then there is a question of how this is to be read, because this is a function of rho. And because that's a function of rho, it is not a priori clear what interpretation you have to have here in order for my noise amplitude to be this. And I require here that this equation would relax to thermodynamic equilibrium, meaning this free energy density that you have here on the right-hand side. This then implies, if you write down the corresponding Fokker-Planck equation, the functional Fokker-Planck equation for this relaxational dynamics that we already had in the dry case, you will find out that the interpretation you need to use in order for the free energy to come out as this is the one by Hengi. It's not Ito, it's not Stotanovich, it's the one by Hengi.
So it's the same as a drive?
Yeah, because that doesn't change. The wet case is just changing the dynamics of the system. It's not going to change the steady state distribution up to kinetic terms which are not important.